What we're going to be doing in this example is estimating the area under this function, x to the third plus e to the x, over the interval from 0 to 2. And we're going to estimate the area using a Riemann sum with n equals 6 boxes and midpoint evaluation. So in the picture, we can see a picture of the curve, the f of x equals x to the third plus e to the x over the interval from 0 to 2. So that curved shape underneath the function over the interval 0 to 2, this region here is something that we want to estimate using a Riemann sum with the rectangular boxes. So the first step is to partition the interval from 0 to 2 into 6 equal pieces. So the partition would look like this. 0 to 1/3, 2/3, 1, 4/3, 5/3, 2. So those would be the boundary points of our subintervals. Dividing this up into 6 equal parts, with 1 being that center value, and then having 1/3, 2/3, 1, 4/3, 5/3, and 2. So the width of all these boxes is going to be 1/3. And that's what we refer to as delta x, 1/3. And so to find the areas, we're going to do 1/3 is the width of the subintervals, and then we're going to have multiplied by the heights of the boxes. Now the heights of the boxes are going to be determined by the functional value at the midpoints of the subintervals. So therefore, the midpoints those values that we call c sub I are going to be 1/6, 2/6, 3/6, 5/6, 7/6, 9/6, and 11/6. Again, we'll make that a 3/6. So those are the midpoints of each of the subintervals, the midpoints between these values that are the boundary points of our subintervals, our partition. And so what we have is the midpoints being 1/6, 3/6, which of course is 1/2, but we'll leave it at 3/6 for now, 5/6, 7/6, 9/6, and 11/6. And those are going to determine the heights of the boxes, because we have on the function f of 1/6, f of 3/6, f of 5/6, f of 7/6, f of 9/6, and f of 11/6. So the boxes are getting taller as you progress up the function. And so I'll go ahead and draw the visual image of these boxes, these rectangular shapes that we have here. Okay, draw them as best I can. And so what we have here is it's of course not going to be exact because they're rectangles, not the curve, but the sum of the areas of these 6 rectangles are going to give at least an estimate of the area under that curve. And so what we're going to do then is we're going to call this A sub 6, meaning the area of the 6 boxes added together, where we're going to have the common width be the delta x. They're all being multiplied by delta x, a common width, times the heights, where it's going to be f of 1/6 plus f of 3/6 plus f of 5/6 plus f of 7/6 plus f of 9/6 plus f of 11/6. All right, we're going to need our calculator eventually to do this, because what we're going to have then is that the area with 6 boxes is going to be a sub 6 equal to the common width of 1/3. Each of the boxes has a width of 1/3 multiplied by the functional value at each. And remember, the function is x to the third plus e to the x. So we're going to have, and I'll go ahead and write this out, 1/6 cubed plus e to the 1/6 plus 3/6 e to the e6 cubed plus e to the 3/6 plus, and then the third rectangle, 5/6 cubed plus e to the 5/6 plus, the next one is 7/6 cubed plus e to the 7/6 plus 9/6 cubed plus e to the 9/6 plus 11/6 cubed plus e to the 11/6. Now that's a lot of writing there, but we have 6 separate heights of rectangles all being multiplied by the common 1/3. Will give you the area of 6 rectangles. Now this involves a little bit of calculator work, so we need to go and enter all this in the calculator. And with your TI calculator, you can enter that in one string. And we're going to get a6 equals 1/3. And going ahead and putting that entire string into the calculator, what I got was 30.91205.147. And that's actually the sum of all the heights. And of course, each rectangle is height times width, and they're all being multiplied by the common width of 1/3. So if I multiply that by 1/3, what I'm going to get then is 10.30401716. And that is an estimate of the area under the function x to the third plus e to the x over the interval from 0 to 2. Again, this is an estimate of the area. Now, as a matter of fact, the actual true area is really close to that. And we'll be seeing that in a later section, how we can actually find the true exact area. 10.389, again giving it to several decimal places. 0.561, and you can see the estimate is actually very good, about 10.3 and a little bit more than 10.3 here.